This is our lesson over 3.5b, Newton's Law of Cooling. As we go down to slide 2, Newton's Law of Cooling is an exponential decay model in which an object is heated to a temperature and over a period of time it cools in an environment that has a different temperature, typically a cooler temperature, and as the object cools, it reaches a new temperature over a period of time. So you can see the formula T equals C plus the quantity T sub 0 minus C times E raised to the KT. The uppercase T is the temperature of the heated object at a given point in time, T. C is the constant temperature of the surrounding medium. We're going to understand that a little better once we do a problem. T sub 0 is the initial temperature of the heated object, and K is a negative constant associated with the cooling object. And that's because it's an exponential decay model. So let's look at this example. It says an object is heated to 100 degrees. It is left to cool in a room that has a temperature of 30 degrees. After 5 minutes, the temperature of the object is 80 degrees. Use Newton's law of cooling to find a model for the temperature of the object T after lowercase t minutes. So when it says an object is heated to 100 degrees, that is its initial temperature. That's T sub 0. And in our model, you can see here, that is plugged in right here, 100. It then goes on and says it is left to cool in a room that has a temperature of 30 degrees. So let me change our color here. The 30 degrees is the temperature of the surrounding medium, and that's the 30 right here and here. Then it says after 5 minutes, so that's the length of time. So the 5 is the time up here. That's the T. The temperature of the object is now 80 degrees. So the 80 degrees is the temperature of the object after it's been sitting out in an environment that is cooler than the heated object. So as you can see, it has to be an exponential decay model because the object is heated to a temperature. It is left to cool in a room that has a lower temperature, and after a given period of time, the temperature of the object has decreased, which in this case, to 80 degrees after 5 minutes. And you can see in the model what that looks like plugged in. So what we want to do next is see how we actually solve that model. So here is our model, and the first thing we want to do is try to isolate the exponential term. There's a lot going on in this problem, so as I look, the first thing I notice is that the quantity in parentheses can be simplified. 100 minus 30 would be 70 times E raised to the 5K. And so the next thing I want to do after I simplify what's in parentheses is I want to subtract 30 from both sides so that I can isolate my exponential term. That's going to give me 50 equals 70 times E raised to the 5K. At that point, I want to get the coefficient of the exponential term to be 1. And I can do that by dividing both sides by 70. When I divide both sides by 70, I get 5/7. 50 over 7 reduces to 5/7 equals E raised to the 5K. At this point, it should look familiar to you with respect to what we did in our previous lesson. To solve and find the value of k, we want to take the natural log of both sides, since the base is e when we deal with the natural log, and on the right side, that's going to all cancel out. So I'm going to come up here. What we now have is the natural log of 5/7 equals 5k. And so to finish solving for k, I'm going to divide both sides by 5. So k is going to equal the natural log of 5/7 all divided by 5. Now keep in mind, your calculator is going to automatically insert that left parenthesis when you enter a natural log. You do want to get in the habit of closing it so that when you divide, you're actually getting the answer you're looking for. And so if we do this, we're going to find that value of k, which I'm going to round it to 4 decimal places. And so k ends up equaling about negative 0.0673. You should test that in your calculator to make sure you're getting the same outcome, but that's the value of k, which means now when I go back to plug into my model, and I'm going to write this below, is going to be t equals the 30 plus 70 times e raised to the negative 0.0673t. And that is the generic model that I can use for problems associated with this situation. I kind of want to say it's our scenario that we have. An object is heated to 100 degrees. It's left to cool in a room that has a temperature of 30 degrees. After 5 minutes, the temperature of the object is 80 degrees. And so our generic equation has the temperature of the surrounding room as 30, and if the initial object is heated to 100 degrees, when you subtract, that is why we have 70 in our model. So now let's see how we use this model. If we go down here, let's look at this example. It says an object is heated to 100 degrees. It is left to cool in a room that has a temperature of 30 degrees. After 5 minutes, the temperature of the object is 80 degrees. That sets the scene. It's the same scene and the same model we just found. So now we have our question right here, which is, what is the temperature of the object after 20 minutes? Now, in this case, for our model, all we need to do is plug in 20 for lowercase t. So I'm going to have t, uppercase T, equals 30 plus 70 times e to the negative 0.0673 times 20. And you can put a dot in between those and let your calculator do the work. Let's round to the nearest degree. And so I think if you enter that, go ahead and try that. But you should end up getting about 48 degrees Celsius. And again, you can pause the video and check that. But after 20 minutes, our lowercase t, the temperature of the object will be approximately 48 degrees. So, does that make sense? You substituted in 20 for lowercase t into our base model, and you found after 20 minutes, it's now 48 degrees, and that kind of makes sense. If after 5 minutes, the temperature decreased to 80 degrees after 20 minutes, it has decreased to 48 degrees. So now, in our final example, let's see a different twist on our scene. So our scene again starts, an object is heated to 100 degrees. It's left to cool in a room that has a temperature of 30 degrees. After 5 minutes, the temperature of the object is 80 degrees. That's just setting the scene, same scene as we saw from the start. The question is, right here, when will the temperature of the object be 35 degrees? So in this final part, they want to know when the temperature is going to be 35 degrees. So that 35 degrees is going to be plugged in for the uppercase T, and we're going to solve for the lowercase t. So I've got, and I'm going to do it over here because I might need the room, 35 being plugged in for the uppercase T equals 30 plus 70 times e to the negative 0.0673 t. And I'm going to start by subtracting 30 from both sides. That's going to give me 5 on the left side equals 70 times e to the negative 0.0673 t. Now, you should know what to do and could go ahead and solve. But what we're going to end up doing is dividing both sides by 70. That gives us 5/70 equals e to the negative 0.0673 t. And then we can take the natural log of both sides, which we know because it has a base of e, that all cancels out. And what we're left with is the natural log of 5/70 equals negative 0.0673 t. Which means if I go up here to solve for t, t is going to equal the natural log of 5/70 all divided by negative 0.0673. And again, when you enter this in your calculator to check, the calculator automatically puts that left parenthesis for the logs. You've got to close it, and then you've got to let the calculator do the work. And in this case, when you round it, it looks like it rounds to 39 minutes. So the temperature of the object will be 35 degrees Celsius in approximately 39 minutes. All right, I hope that helps you understand Newton's law of cooling. It is an exponential decay model, which is why it's included in section 3.5. You will see I assigned, I believe, 4 problems in my math lab. I made it a small number because they are multi-part, and it's piggybacking on what you were assigned on Monday in 3.5a, or on Tuesday, I mean. So anyhow, you want to finish 3.5a and complete 3.5b as well, so that you have section 3.5 under good understanding. And then Friday, we will be doing our review. I have a review worksheet packet that you'll complete to get ready for your quiz. Hope that helps, and we will talk to you soon. Thank you.